Welcome to Crescent Offshore Observations Special Interest Group meeting to discuss SZ4D priorities offshore in Cascadia. For people who've been following along, we had a meeting in November when Diana Roman presented, and then we had a lot of discussions about the sort of scientific priorities for offshore observations for GNSSA and APG observations, but we didn't get as far as talking about specific sites, but we agreed at that time that we would have a meeting to do so. Then there were discussions. There was an SZ4D meeting before the USGS meeting for discussing Cascadia and Alaska plans in general. And then there was a offshore observations lunchtime SIG at the USGS meeting where we discussed it briefly. But today we get to discuss deployment ideas. And this is just one slide from Dana Roman's presentation. SZ4D, as part of their infrastructure proposal, plan to request about 9 GNSS APG sites offshore Cascadia. They had a tentative plan to put these in 3 corridors, but invited ideas from the community, and that's what we're here for today. So we have a pretty packed agenda, and I think the goal for today is just to compile ideas for deployment sites. It's not to reach consensus, but to provide everybody's ideas and views to SZ4D so they can move ahead with their plans. And so without further ado, I'd like to introduce the first speaker, who's John DeSanto, and I'm going to ask all speakers to stick to 8 minutes so we can get through this agenda. And John's going to talk about it, give us a quick update on GNSSA results in Cascadia.
Okay, can y'all see that?
Yes.
Okay, good. So I'm John DeSanto at the University of Washington, and I am going to try and move fairly quickly through this. To start with talking about GNSS acoustic, these are the instruments, of course. We have the seafloor transponders. We drop these off the side of a ship in arrays of 3 in an area of interest. And then about once a year, we deploy a wave glider to each array to survey the transponders acoustically. You resolve the location of the transponders relative to the wave glider acoustically, and then you can use GPS on the wave glider in order to anchor the whole thing in a terrestrial reference frame. I'd hope we'd all know this by now, but good to have a little reminder. So as for deploying these instruments in Cascadia, it's probably best to talk about quote unquote generations of surveys or of arrays that have been deployed, because there are quite a few experiments that have been conducted in the region. So shown on the left here is the first of the arrays that I personally was involved in. These sites were deployed in 2016 and 2018 by Dave Chadwell and David Schmidt. And the basic gist is that their goal was to try and resolve shallow locking near the deformation front of the Cascadia subduction zone. And particularly, there is longstanding modeling of fault locking that predicted that there would be a decrease in locking near the deformation front offshore Oregon. And so the north-south span of this array was to try and capture that larger locking in the north and see a decrease off of Oregon in order, as was predicted by the models. After 7 years of collecting data, these are the velocities that we were able to resolve. That's not 7 years of measurements at each site. There is actually a sorted history of which transponders were where that we don't have the time to get into right now. Suffice to say, we actually have fewer transponders than sites in this array. And so we've had to shuffle things around a little bit in order to make sure we got proper coverage everywhere. But the main conclusion, these are in review in EPSL right now, is that these sites are very much moving with the downgoing Juan de Fuca plate. This vector here is Morbel for reference of the Juan de Fuca plate motion relative to North America. And we can see that, even though these sites are resting on the North American plate, they're moving with downgoing slab, which is, evidence that we might be seeing a reasonably high locking fairly close to the deformation front of the subduction zone. So moving forward, a few years ago, now we NSF funded the acquirement of a large community seafloor geodetic instrument pool. This included some 50 GNSS acoustic transponders, enough to establish 16 sites. In 2021, there was a workshop, much like this one, in which many of us gathered together in order to discuss where we wanted to deploy these transponders as part of the community experiment. The results of that meeting are shown in this figure here, and that was to deploy 6 new sites in Cascadia, denoted by these red circles. I will stress that these were not final positions. Actually, once we acquired these rough dots on the map, these were then included in a proposal to NSF that got funded, and afterwards a smaller group of PIs met in order to do a more fine scale siting and assess where on the seafloor in the rough vicinity of these chosen site locales we could feasibly deploy an array. And in 2022 and 2023, we were able to deploy those sites. So if you compare the figure from the previous slide to this figure here, just locations of the triangles, you can see that I think we were able to adhere pretty closely to what the community stated it desired in that workshop. And now we've been collecting annual positions at those sites for about 2 to 3 years. And so this is a figure that I presented at AGU this past December, showing the preliminary velocities. These are 2 and 3 year velocities, which means they're based on 2 or 3 positions. I wouldn't put too much stock into them, but it is nice to see that we are collecting data in an operational capacity, and we have every intent to go back this summer and subsequent summers until the first part of the community experiment wraps up in 2027. So these velocities are specifically every position collected since 2022, when the first of the community experiment sites were deployed. And so there is some disagreement with the sites that, or the velocities that I presented earlier, which were from an earlier time period. I will note that we do have this hole in our coverage here at NGH1. That's because the previous array was folded into the community experiment. And like I said earlier, we have fewer transponders than sites in that array. And so that still holds true in the community experiment. I know that this site NGH1, reoccupying it, the concrete benchmarks are on the seafloor, so we can do that with an ROV. And I personally think that it should be a high priority to get transponders back down there. I don't know if other PIs in the community experiment share that opinion, but I suspect they do. So I will just leave that seed planted. There are 2 other arrays that are worth mentioning in Cascadia. The first is an array north of the border off of British Columbia. This is maintained by Ocean Networks Canada. Martin Heisman and Jesse Hutchinson have done a lot of work deploying and surveying these sites for the past few years. Unfortunately, I don't have any vectors from them to show to the group today, but I look forward to their results as they collect more data at these sites. Another array that has been deployed to the south. This is off the Gorda Plate by the USGS, and they've collected, I think, their second year, maybe third, of positions recently this past fall. And so once again, still early going for this array, but as more data is collected in the coming years, we'll get more information from these sites in the south. And so kind of an integrated viewpoint of what all of the GNSS acoustic information that we have in Cascadia currently looks like is shown on this figure to the right. These I've plotted velocities where we have them, and in this particular figure, I've tried a first estimate of combining the Chadwell and Schmidt GPS acoustic velocities between 2016 and 2022 with the community experiment velocities. And of course, as we collect more data in the coming years, I expect these velocities to change, bring these very large ones down, I hope. It's an ongoing process, and but yeah, in the past 5 years, we've gone from having like 4 sites offshore Cascadia to nearly 20, which is pretty cool. So that's really where we stand currently, and yeah, look forward to hearing folks' opinion on where to deploy the C4 the SZ4D sites. So I'll leave it at that.
Thank you, John. Next up is Andy Newman, who's going to be talking about GNSSA resolution analysis in Cascadia.
Andy, you're on mute.
You'd think I'd know how to do this by now. Sorry about that. Okay, so I am going to talk about resolution analysis, but I'm also giving an update for SZ4D's plan. So I'm going to do a little bit of both, and it's going to be tough to do it all in 8 minutes, but I'm going to go as fast as I can. So we are leading this effort for this MSRI2, and just really quickly, there's the PI team, or the senior personnel team as it stands right now. So I myself am representing the offshore infrastructure, the U.S. component of the offshore infrastructure on this project. As a reminder, for SZ4D, a plan is to include 20% of instrumentation and 40% of activities in Cascadia, with the bulk of the infrastructure going into Chile. I don't want to really belabor this. One thing, you've seen this before in the November meeting. One thing that we started talking a little bit more about coming off of our Chile meeting that we had this last month was, instead of really considering these as phase 1 and phase 2, we're leaning more towards like a lens 1 and lens 2, with the idea that maybe a wide aperture and a narrow aperture, but much more detail image could be done at the same time. In our discussions, we looked at, for Cascadia, having around 9, the numbers that we've been passing around now are between 9 and 12 GNSS-A plus calibrated pressure sensors, what we often know as the AZA pressure sensors, deployed in Cascadia. And so it's really the central line here that I wanted to focus on. In the interest of time, I'm going to skip the scientific questions. I think we're probably pretty well versed in that. To get into the resolution analysis, I wanted to first start off with some of the work that we've done in Chile. So this is looking specifically at Chile using SLAB 2.0 structure, putting in errors like we think are reasonable for GNSS acoustic, which is 2.5 centimeters horizontal errors. Vertical errors are just blown up dramatically, so they don't get counted in sort of inversion, and then resolve for 3 years of convergence. And so in Chile, that's about 20 centimeters, just a little bit underneath it. We evaluate both what's called the resolution spread, which models how big of an area, or how large a resolvable patch you can get on the fault. And so that's what's color contours on the fault itself. And the other is the approximate sort of data value. And this comes directly out of the data resolution matrix. And so redder colors are higher value than, let's say, the light blue colors. Okay, just as an example, we have 45 stations that we find in our optimal geometry for Chile. If we put in now, using that sort of resolution test, we put in now a series of different forward models, put noise in the synthetic data, and then try and recover an inversion. You can see that we're recovering quite well those sorts of signals. Here's just another example using larger blocks. Particularly what's important is evaluating the near trench coupling behavior that you'll see between model geometries. Okay, so moving back to Cascadia, the idea was, and we just saw this figure before, considering 3 transects in the northern, central, and southern segments. All of them have variations in upper plate faulting, but as we move along the megathrust, as we go to the near trench region, the northern segment looks to have the largest, first off, the largest offshore segment, but also probably the largest and possibly near trench locking due to prior models. Central section has more variation in locking offshore. The southern section also seems to have a lot more relationship with, I guess, with ongoing seismicity and certainly association with the Mendocino Triple Junction to the south. Okay, so I know I'm going really fast. These are some very preliminary models using SLAB 2.0 for Cascadia. Just really quickly, on the left-hand side would be our resolvability or resolution if we had no seafloor geodesy whatsoever. And so if you see these white areas, that means that anything you're capturing there, you're resolving there, you're actually really sampling areas greater than, and in this case, actually probably much greater than 200 kilometers. Once we put in those stations that John just really nicely described, that includes the previous USPI instruments, the community experiment instruments, those by the USGS and some Canadian sites, includes 21 stations in total. If all of them are operational, then we get a resolvability as such, which actually looks quite good. But we'll see that there's still really large areas that are red, where red to white mean that 100 or greater kilometers of spread over the environment. Okay, so the one that was on the right is now on the left. What you see here now is just an a priori densification, now also incorporating those AZA style APGs. And so in some initial communications with Eric Fredrickson and Matt Way, the argument is that we can probably say that we have about 1 centimeter of vertical resolution with those instruments. So I put those errors in for the vertical as well as the horizontal, and added a bunch more stations around those 3 different transects. I'm going to zoom in really quickly and talk about each one individually. So if I added 10 sites in the northern segment, I should say these are the red blocks that were shown on the previous map. I ended up putting some just outside of that to the north, but as I said, this is very preliminary, just a starting point for considerations. But once we do that, we can now see that we can resolve patches that are on the order of between 20 and 40 to 50 kilometers across the region. As we get nearer land, we don't do as well, and that's in part because without using a trawl-resistant design, we can't really go shallower than about 1,000 meters water depth. So these are all these points I should note are looking at the bathymetry to characterize what is feasible or not. Okay, central segment, I've added more stations than what we had planned, but this is kind of giving you a range. Again, I went a little bit further outside. I should say again, the squares that are offshore are new potential sites. The triangles offshore are existing stations in the region. But you can see again, we're starting to get really high recoverability on the order of 20 to 40 kilometers across most of that region. Similar in the south, here's another projected plan. In some of these cases, we have even stronger densification where you get really high resolvability. And just because of a little bit of discussion last time, I did include one on the Pacific plate, so south of the triple junction, because if you're so close, why not do that? Questions may come across as to whether or not that's really subduction zone related or not. Anyway, that's the discussion point. Okay, so wrapping back up, SZ4D is planning from this MSRI. It's a large $100 million project. We are currently, as our initial planning goes, over budget, so we do need to whittle down in some respects. Let's not worry about that so much here for this discussion, but don't try and expand beyond our prior plans. If you want to get more involved, you can go to the new infrastructure planning webpage, which is there, which is listed there, as well as you can email any of the leads for the infrastructure, particularly offshore infrastructure related to this group. And with that, I think I hit my 8 minutes.
Great. Thanks very much. That was perfect in timing. So now we get into the presentation of specific ideas. And we're going to have 5 presentations, and the first person up is Surey Shia.
Hi, everyone. I'm going to talk about the potential sites from engineering perspective. All right. This is a figure from Fred Spies. This figure illustrates the standard configuration of GNSS to make precision geodetic measurements. There are a few assumptions. In general, Spies' philosophy of obtaining highly accurate and safe flow displacements is that we have to combine observations to form symmetric observations in order to cancel out errors mainly associated with the variable ocean. Following that, GNSS has been practiced, and then the typical configurations using 3 acoustic transponders deployed in an equilateral triangle. And then, well, if you have more transponders, let's say 4, you can form a diamond shape. In general, we believe the ocean is largely horizontally stratified. And then if the transponders, they are deployed symmetrically. And then the acoustic rays, the curvature, they would have similar bending characteristics so that we could cancel out the noise due to inaccurate sound speed model. So we have to find a flat surface in order to make the geometry symmetric. And then this really affects the precision we could obtain from GNSS measurements. So here, this figure on the left, this panel illustrates an array deployed on a flat surface, so that if the ocean is really horizontally stratified with many different layers, then inaccurate sound speed model would affect acoustic rays equally, so that if we calculate the displacement, let's say horizontal displacement by decomposing the range residuals, then the horizontal directions, the errors would be canceled out. So it's insensitive. The arrays displacement is insensitive to errors in sound speed model. However, in many places, particularly near the slope of the full arc region, sea floor relief may affect the precision of GNSS. So the second panel illustrates an example where two transponders are deployed at the same depth, but the third one is deployed at a greater depth. And then here, the quotients to estimate the error due to this actual water column. Well, I made some assumptions. For example, if sea floor has a certain relief, the ocean's layers might not really be horizontally stratified. But then to the first order approximation, I think this is reasonable. And we can calculate the error. It is a function of depth difference plus the sound speed bias. And then here I divide this by 3 because we always decompose the range releasers among 3 transponders. Well, if it is a 3 transponder array, so that's why I divide this by 3. And on the right panel, this panel illustrates the error caused by just simply by inaccurate sound speed model in a case where there's difference between transponder deployment depths. Well, this figure, the error tolerance, it has excluded all other possible errors, including GNSS positioning error and some other errors like the attitude. So this is the ideal case. From this figure, you can see that in order to limit the error in within, let's see, 2 centimeters, we have to limit the depth difference to be under about 80 to 90 meters if the sound speed is accurate, sound speed model is accurate to 1 meter per second. Well, the smaller the depth difference, the more wiggle room, the more the higher chance we could obtain more accurate sea floor displacement measurements. So I think it's important to identify the errors that are suitable for us to limit, to reduce noise from the stage of instrument deployment. On this slide, the left panel shows the bathymetry of this region, and the middle panel shows the standard deviation of the 3 transponder array configuration.
For 1 minute. So
for those local minimums, these are the places where I believe are good for high precision GNSS measurements. And these gray areas are areas with water depths deeper than 3,000 meters, which is the depth rating of typical transponders. This is an example of a site here. I did some resolution test. Well, Andy already gave a very nice presentation of the resolution test. So in general, this will improve the resolution, I think. For water shallower than, let's say, 1,000 meters, you might have to consider to use a trough resistant design. Mark Zamberger and I, we have done a project to develop this type of benchmarks, and we tested it in San Diego in a pretty busy offshore area, and I think it works fine. Data quality is pretty good, and I think we can use that. All right, that's all. Well, I left pictures from Ben Brooks and Todd Erickson from USGS. They had a transponder deployed at about nearly 1,000 meters, but then it was caught by a fishing boat.
Thank you.
Thank you.
So next up is Janet Watt.
Sorry, just a minute. Can you see it? Can you guys hear me?
Yes.
Yes.
Can you see my screen?
Yes.
Yeah.
Okay, great. Well, thanks, Surya. I'm here representing the USGS instrumentation, and I'm going to focus down in the Gorda Plate where the USGS has their 3 transponders, as John mentioned, and we're hoping to get a 3rd measurement on the Gorda Plate site this summer, so then we can start talking about vectors. So again, we're zooming in on the Gorda Plate here in southern Cascadia, and the primary science goals for the USGS here are to constrain Gorda Plate kinematics and shallow megathrust locking and its variation along strike in southern Cascadia. And I've zoomed in on this portion of Cascadia in the map on the right and showing the 3,000 meter depth contour in purple and the 1,000 meter depth contour in green. And you'll see the hexagons are the existing sites in southern Cascadia. And I just want to mention that the USGS does have 2 additional GNSSA sites that we are planning to deploy this summer. And we have been discussing where those are going to be located. And our primary targets for those 2 stations are shown in the yellow stars to be placed on either side of the deformation front south of the existing stations to try to capture differences in hypothesized locking from north to south, where the Gorda Plate is subducting, we think, under the North American Plate. We do have a tentative site, again, like Andy, on the Pacific Plate, south of the Triple Junction, because it would be good to know exactly what the Pacific Plate is doing there to understand Gorda. And here I'll just show, this is, so the 1,000 meter trawling line is sort of an estimate, a conservative estimate. As was mentioned, we had a transponder station trawled up, and it was by a NOAA. It wasn't by a fisherman, commercial fisheries. It was by NOAA.
Sorry about that.
That's okay. Don't worry. Yeah, but it and it was shallower than 1,000 meters. But this is just a map I found online, and I've seen similar. This is trawling. On the right, you see relative intensity of commercial bottom trawling, with red being high intensity and green being low intensity. And so I've just placed that on top there, just giving us a little more wiggle room, perhaps, depending on how risky you want to be with attempting trawling in these areas. In terms of potential for SZ4D to expand and build upon what we've done, I'm showing proposed sites for SZ4D GNSSA station shown in the pink stars. And 2 of these are to expand GNSSA locations in sort of a transect form to focus in on the Crescent, offshore Crescent City, to get a better idea of locking in that area in sort of a transect form, in addition to filling in along strike potential variability in locking there with a site near Trinidad Canyon in between the USGS site locations. And again, just to argue for making sure a portion of these sites go in southern Cascadia, I will argue that the pros of putting stations down here are that there is actually seismicity in this portion of the margin, and there is a chance of capturing coseismic displacements with these geodetic stations. There's also variable morphotectonics and estimated locking along strike, and capturing the possible transition from subduction to transform motion. There are also, in addition, a number of leveraging opportunities, which I've listed here. Cal Poly Humboldt has a new vessel that is capable of going out of Eureka and accessing these sites. USGS has GNSSA stations here and will be operating here and will be available to collaborate potentially on ship time and wave glider ops in the area. USGS also has high resolution seismic and AUV imagery along the deformation front that can provide geologic context to some of these GNSSA stations. I'll also mention that there's a NEHRP funded study by Brandon Schuck et al. To provide velocity, structure, and fault geometries by reprocessing legacy data in this area because the KZ21 survey did not extend into California. There's also onshore USGS GORDAS study led by folks at USGS, Jeff McGuire and Andy Barber. They have a co-op with Cal Poly Humboldt to expand onshore DOS to further constrain upper plate structure in this area that can be related to the megathrust. And there is potential for access to offshore telecom, wind farm cables to extend this DOS capability offshore. But of course, the cons in this area are that it is tectonically complicated and some people choose to avoid it. That's all I got.
Great, thank you very much. Helping us catch back up on time. So next up is John DeSanto again.
Okay, so I don't have a PowerPoint prepared, but this is a PDF that I uploaded to the link that William posted in the chat, so anybody can go and read this for themselves. So here I have a map that I've created using all the previous GNSS acoustic sites that I showed previously in my presentation. So the yellow triangles are sites that already exist. The red sites are sites that I am proposing for SZ4D deployment, and the orange sites are sites that already exist but are not currently occupied by transponders. So let's go through the justification really quickly. First thing is some boilerplate. As Suri helpfully explained, there are a number of engineering concerns that go into siting GNSS acoustic arrays in places that have better chance of yielding precise measurements and also of not being trawled up. And so I have done like a quick sweep in order to try and site these in valleys that are deeper than 1,000 meters in an effort to make sure that we can collect or maximize our chances of success with the deployments. As for the 3 quadrants that were proposed, I tried to deploy like roughly 3 in the north, 3 in central, and 3 in southern Cascadia, according to the rough SZ4D plan. To go through the individual sites, I'll start with the orange triangles here. This site on the Juan de Fuca Plate was deployed by Fred Spees and Dave Chadwell back in the 90s and has roughly a 20-year time series of unpublished positions between 1998, 99, and 2014. And so my idea here is that if we were to return to this site, it's a 4 transponder array, so it'd require using a spare in the instrument pool that the SZ4D will acquire. But if we go here and collect another 1 to 2 years of positions, the previous positions collected by Dave Chadwell are archived in local systems at UW and at Scripps. And so we could leverage about the 12 or 15 or so years since the last time it was studied in order to really refine what the velocity of the downgoing plate is. And then after like 2 years or so of measurements, we could recover the transponders and then move them to another unoccupied array off of Grays Harbor, Washington, that I pointed out before in my previous presentation, and start collecting positions here. This site hasn't been surveyed since 2018. So once again, that large time gap would allow us to pretty easily refine a velocity in a region that right now is like a big hole in our coverage. As for the science justification of the other red sites in northern Cascadia, and really throughout, my goal is to try and not only constrain the velocity near the deformation front on the North American plate, but also to try and pin down roughly what the velocity of the downgoing subducting plate is. And so we have a site offshore here on the Juan de Fuca side off Washington, to fill in a relatively huge gap between the sites off British Columbia and off of Newport. And then on the accretionary prism, my goal was simply to increase our long dip coverage and bring some sites further near to the deformation front where the accretionary prism is widest. In Central Cascadia, we have the OOI cables that are coming out, and our goal is simply to try and get more sites closer to the cables and any instrumentation that might be there. And so simply increasing along strike coverage. There's a site up here, and then a site just to the east of Hydrate Ridge, and that's to try and leverage any instrumentation and like DAS or pressure that or other like OBS that happens to be cabled in that region. Towards the south, the considerations are to one, get a sight on the Gorda plate and increase some along strike coverage. Another consideration is that if we were to go south of the USGS sites, a worry that I had was that it would be a very large detour in order to get a wave glider from the southernmost community experiment site, which I assume the community experiment would be folded into SZ4D. That might not be a good assumption, but please bear with me. And my assumption was also that it might be more expedient to allow the USGS to expand their array to the south, as Janet mentioned, and so just trying to keep things slightly independent. I thought that it would be more expedient to try and fill in some of the gaps in the north. And so a big one is trying to constrain what is the Gorda plate doing as it subducts. And so there's this fracture zone that Janet had mapped out. We have a site to the south of it, and my idea is simply deploy a site to the north of it, and then also a site on the Pacific plate side so that we have an anchor, and so we can both try and resolve the spreading rate here at the Gorda Ridge and also the internal strain on the plate across this fracture zone here. And really, those are my thoughts. So yeah, thank you.
Hey, thank you so much. And so next up is Noel Jackson.
Hi, everybody. Do you hear me okay?
Yep.
Okay. Well, I also am basically just sharing a Word document. It's a slightly modified version of what I uploaded. But I am, and pardon me, I didn't really prepare too much. I'm just going to kind of run through what I wrote down, what my thoughts were. So I've proposed 9 sites here that I've labeled P1 through P9 for proposed sites 1 through 9. And I sort of roughly put 3 northern sites, 3 central-ish sites, and 3 southern sites. So I'm just going to give my thoughts on the placement, kind of northern, central, and southern, and then talk about some other related thoughts that I had about good placement for these sites. So these are 2 of the base maps that we were provided. The one on the left has one of the newer coupling models and various seismicity for the region. So starting with northern Cascadia, if we just look at those P1 through P3 that I've suggested, those are essentially because there is a large coupled or locked patch up there that clearly is a megathrust danger, and our current coverage of that locked patch is not very dense, especially compared to the Canadian network just to the north. So it's to increase density there, but also P1 and P2 are specifically shallower, above a shallower part of the subduction zone in deeper water. But to get at the coupling in the near trench region up there to see if it is in fact fully coupled to the trench. And then P3, again, it really is just kind of filling in a gap in the network there. P4's site selection, going further to the south, was chosen for a few reasons. One is that there are detected VLFEs in that particular region, and another probably related reason is that it's right on kind of a coupling transition along strike there, where we transition from the northern segment to the central segment, and you can see it's in that transitional part of the coupling on the map on the left. So that I think it's important to look at coupling transitions, in particular how sharp that coupling transition is, because of course the gradient in the coupling transition gives you the strain and then the stress buildup. So I think getting at the gradient at the base of the coupling or lock zone is important. So that's why P4 that and the VLFEs for that site selection. Going further to the south, P5 was chosen for a few reasons. One reason is because there are both detected VLFEs offshore, but also these 2 swarms that were detected with some of the newer papers using the OBS deployments in that region, and they've been interpreted as subducting seamounts. And the other thing you see there is that the coupling, and this is not unique to that particular coupling study, but it's been seen for over a decade, the coupling in that region is not fully coupled to the trench in this model. And we see this low degree of coupling, but also this really broad coupling transition, where we have this really broad zone of partial locking or partial coupling in there, associated maybe with the location of those subducting seamounts. So there's some interesting potential coupling stuff going on there, and that's why P5 was selected. Additionally, its location close to the existing cable could be helpful in terms of that's somewhere where ships need to go out to service things on the cable anyway. So that could be a convenience factor. Going further to the south, P6 really, again, is just filling in a gap. And again, this is a region where we have lower coupling, and I think getting at, what is the coupling in Central Cascadia really is important for answering the question, can we rupture through northern and southern Cascadia through Central Cascadia at the same time, or is Central Cascadia right now sort of a barrier to rupture? And so that's sort of why P6 was chosen to fill in that gap. Going further to the south on the Gorder Plate, I have a slightly different proposal. So I've put 3 sites in there, and maybe it's better to look over here with what I've done. So I've taken something that looks like the pair of sites that are in the USGS network that span the trench and copied it down to the south, and then added another site on the other side of the Gorder Plate. And the reason that I did that, similar logic to what John was presenting earlier. So the idea being that we know there's internal deformation of the Gorda Plate. We want to get at that. here is a network of baselines that we could make with 3 new sites plus the existing USGS sites. And with these baselines, we could get at some strain tensors in this region, which is why I've made a baseline map here. The trench spanning sites are because with the internal deformation of the Gorda plate, we just really don't actually know what the convergence rate is at the trench. And if you look at the coupling models, like going back up, we do have an area of strong coupling around southern Cascadia. This is also an area with a lot of background seismicity, and also the area where the paleoseismic record says it might rupture most frequently. So I think from a hazard standpoint, southern Cascadia is really important. And the Gorda plate is really important, and we just really don't understand it. I have selected these 2 sites to give us a convergence rate and a coupling estimate further south along the Gorda plate. I've tried to go compromise where I'm going further south towards the triple junction, but still trying to stay far enough north that there won't be too many large earthquake offsets. Because of the background seismicity here, it is definitely worth thinking about the fact that we have magnitude 6, 6.5 earthquakes, maybe even getting up to 7s every few years. And with a 1-year sampling rate, that definitely is going to alias into our time series. So I've tried to select sites that are far enough north that they won't be aliasing too many earthquake offsets into them. I also do think averaging through earthquake offsets in a region that has lots of earthquakes is maybe okay anyway. But that is something worth thinking about. So I guess one last thought I had, which actually didn't make it into the document I uploaded, is that, per Eric Fredrickson's work, I'm very convinced by what he's calling the isobath method. So for the pressure sensors, if we want to look at slow slip, which I think is important, the pressure sensors give us a continuous measurement, but the signal to noise ratio is much better if you can difference them with pressure sensors at the same depth. So I have kind of made some suggestions of sites that we could pair match for depth matching. So for each of my suggested new sites, except for P5, I've kind of suggested a match site, either one of the new ones or one of the existing ones, where we would try to match the depth. And the idea here is that if we have slow slip events in Cascadia, they tend to migrate along strike. So even if the same slow slip event is seen by 2 pressure sensors, say these 2 up here, because of an all along strike migration, it would likely be at a different time. And so we would hopefully see that in the difference time series. So that is pretty much all my thoughts on site selection. And I guess I'll just leave it with, this was my overall proposal that I landed on.
Thank you very much, Noel. And so finally, Kellen Wang.
Thank you. It's a nice slide. It's slow. Can you see my screen?
Can you hit the swap displays button up at the top?
Oh, okay. Okay. Or use slideshow. Better?
You see nothing now.
Now it's black.
Nothing?
Nothing.
Oops. Yeah. Sorry about it. Have to restart it. Can you see it now?
We see it in presenter view, so I don't know.
Okay, so let me just do it again. Better?
Yeah.
Yes.
Okay, okay. Sorry about it. Yeah. And good morning. Yeah. The first oops. Guess, yeah, the first site, oops, is it the right mode? Yeah, okay. Yeah, the first site we'd like to propose is to monitor wedge deformation for this competent part of the wedge. And this is mapped by KC21, and this part of wedge is kind of special. It seemed to have a higher rigidity, and so proposal is the basal fault may be dynamically weakened during a rupture to enable trench breaching slip. And alternatively, it could also be persistently weak with intermittent intraseismic creep. So that's worth monitoring. And the other side we propose is here, that's to monitor. And this part, that's also based on KC imaging, KC21 imaging. And this yellow bar shows the only area along Cascadia where a thick section of sediment is being subducted. And also this red dots show the subducted seamounts mapped by KC21. And so this section with sediment subduction and seamount subduction and with apparently some not fully logged here. There's some correlation here. And so it's worth taking a look and with a fairly short baseline to see whether there is any creeping or intermittent or persistent creeping behavior there. So if you call these first two groups, group 1 and group 2 and group 3 is a lot larger, includes practically all the sites plus many of the proposed sites on the incoming plate. And the reason is there's a real need, we think, to constrain plate kinematics and megathrust locking affected by a melt-rich lithosphere-asthenosphere boundary, LAB. So let's to show why this is important. Let's first go to a Japan trench. With numerous GNSS measurements, including a lot of seafloor measurements recently, it's beyond any doubt that a melt-rich LAB or weak LAB beneath the incoming plate, subducting plate, is needed to explain the post-seismic deformation, many aspects of deformation. And so that's for post-seismic. And if the presence of LAB at Japan Trench is based on limited observations, it is a real matter for Cascadia. And for Cascadia, oops, and this is the LAB is pretty well mapped for the entire Honda-Fuca plate, incoming plate. And also there's a recent work to extend it after subduction based on this land-based array. So there is indication it may continue after subduction. So presumably if it's melt-rich, it's something like that. And if it's melt-rich, it'll be very weak, just like Northeast Japan. And it'll play an important role in plate subduction and earthquake cycle. Therefore, we designed a model to test this like that. And Honda-Fuca plate is the only incoming plate in the world with LAB so thoroughly imaged. And because of the Honda-Fuca plate is young and thin, the effect on earthquake cycle deformation of the LAB is expected to be stronger than any other places. And there's also implications to understand earthquake megathrust locking as shown here by these testing models done by E.J. Zhu. And you can see the variation in earthquake cycles. And this is therefore vertical and horizontal at different times of the earthquake cycle or intraseismic period. And you can see how it varies with time and the difference with or without LAB. And importantly, and the bottom panel It's relevant to Cascadia because 3 years after the previous earthquake, assuming 500 years cycle, if you look at the trench, this is the horizontal velocity. And the trench velocity here with this blue line is slower than the actual plate convergence, the rate you infer from plate convergence by about 20%. And that's because the LAB allows the incoming plate to be shortened, just like the ongoing plate during earthquake cycles. And if we were to use an elastic model, backslip elastic model to model this, and that's what we would produce with 100% locking. If you use 80% locking, we produce this, something comparable with the model with LAB. And so I think that's important. It kind of changes our perception or view of megathrust locking for Cascadia and how we develop locking models, coupling models, and for earthquake hazard. And these two sites here, and I think this is pretty obvious, and we have so many other observations like land stations moving around for different various reasons and severe deformation of the order plate. And it's a pretty obvious observation gap that we don't have any geodetic constraints on the motion of this important boundary. So I'm pleased to see that USGS will have a site somewhere there, but I would prefer the site to be a bit away from the triple junction, something like that. Okay, and if we add one more site here, and that will allow us to somehow study whether this Blanco fault, that activity, affect the megathrust in any way. We don't really know, but it just appears, and there's so much earthquakes here, so many earthquakes, so much seismicity, and there's the apparent low degree of coupling, and to know how it moves and how the plate deforms and how it creeps or locked, and it's important here. And if there's more funding, and we would hope to have 2 more sites, and that site has similar role to P01 here, but potentially could be linked to a cable for continuous monitoring. And this one, it'll form a kind of a transect, and to check if there's any modern signal of the severe deformation of the Gorda plate as described by Janet and Noel. That's it. So we have all these sites proposed. Thank you.
Thank you, Kellen. I'll just share my screen. Okay, so now we're moving into breakout groups, and so we'll split into 7 breakout groups, and